When working with low-voltage lighting loops and dual-coil transformers, the manufacturer advises that looping from one transformer circuit to the next is generally correct. The crucial factor to consider, however, is that the total load on the entire loop should not exceed the total wattage rating of all the transformers combined. For instance, if you are using two 300-watt transformers, the aggregate load on the loop must not go over 600 watts. The primary reason for looping the transformers together is to increase the load handling capability of the loop itself. This is because the transformers are now working in parallel to share the electrical load. Moreover, this configuration contributes to a better balance in the lighting levels across all the fixtures connected to the loop. This improvement occurs because the transformers can more effectively allocate power to those fixtures that require it most, leading to a more uniform distribution of light. When installing low-voltage lighting, it is critical to understand the basic principles of electrical circuits and how transformers work. A transformer's main job is to step down voltage, often from a standard 120 volts or 277 volts alternating current supply to a lower voltage, typically 12 volts or 24 volts, which is safer and more suitable for landscape lighting or other low-voltage applications. Dual-coil transformers have two separate windings that can be wired independently or in parallel. When wired independently, each coil acts as a separate power source, each with its own maximum wattage rating. When wired in parallel, the total wattage capacity of the transformer is the sum of the individual coil wattages. This is where the idea of looping comes in. Looping refers to the practice of connecting the output of multiple transformers to a single continuous circuit that powers multiple light fixtures. This can improve the overall performance and reliability of the lighting system, but it also requires careful planning and execution. One of the main advantages of looping is that it helps to distribute the load more evenly across the transformers. In a non-loop system, each transformer is responsible for powering a specific set of fixtures. If one of the transformers fails or is overloaded, those fixtures will go dark. In a loop system, the remaining transformers can pick up the slack, ensuring that all the fixtures continue to receive power. This redundancy can be especially important in applications where consistent lighting is critical, such as in security lighting or emergency lighting systems. Another advantage of looping is that it can improve the voltage stability of the system. The voltage at the end of a long run of wire tends to drop due to the resistance of the wire. This voltage drop can cause the lights at the end of the run to be dimmer than the lights at the beginning. In a loop system, the voltage drop is minimized because the power is being supplied from both ends of the run. This results in more consistent brightness across all the fixtures. However, looping also introduces some potential challenges. One of the most important is ensuring that the total load in a loop does not exceed the combined wattage rating of the transformers. If the load is too high, the transformers will overheat and potentially fail. It is also important to ensure that the wiring is properly sized to handle the current flowing through the loop. Undersized wiring can also overheat and cause a fire hazard. To calculate the appropriate wire size, you need to know the total wattage of the fixtures connected to the loop, the voltage of the system, and the length of the wire run. You can then use Ohm's law to calculate the current flowing through the wire and consult a wire sizing chart to determine the appropriate wire gauge. In addition to these technical considerations, there are also some code requirements that you need to be aware of. The National Electrical Code, or NEC, provides detailed guidelines for the installation of electrical systems, including low-voltage lighting systems. It is important to consult the NEC and any local codes before beginning any electrical work. Some key NEC articles that are relevant to low-voltage lighting loops include Article 411, which covers low-voltage lighting systems in general, and Article 725, which covers Class 2 and Class 3 remote control, signaling, and power-limited circuits. These articles provide requirements for wiring methods, overcurrent protection, and grounding. When installing a low-voltage lighting loop, it is important to follow these best practices. Firstly, start by carefully planning the layout of the system. Determine the number and location of the fixtures, the wattage of each fixture, and the length of the wire runs. Secondly, choose transformers that are appropriately sized for the load. The total wattage rating of the transformers should be at least 20% greater than the total wattage of the fixtures to allow for future expansion and to prevent overloading the transformers. Thirdly, use appropriately sized wiring for the loop. Consult a wire sizing chart to determine the appropriate wire gauge based on the total current flowing through the wire and the length of the wire run. Fourthly, install overcurrent protection devices such as fuses or circuit breakers to protect the transformers and wiring from overloads and short circuits. The overcurrent protection devices should be sized appropriately for the transformers and wiring. Fifthly, ground the system properly to protect against electrical shock. The grounding conductor should be sized appropriately for the system and should be connected to a grounding electrode system that meets the requirements of the NEC. Sixthly, use weatherproof connectors and enclosures to protect the wiring and transformers from the elements. This is especially important in outdoor applications. Seventhly, test the system thoroughly after installation to ensure that it is working properly. Use a multimeter to check the voltage at various points in the loop and to verify that the current is within acceptable limits. Furthermore, regarding the use of dual coil transformers in low voltage lighting systems, there are several key points to consider to ensure safe and efficient operation. Dual coil transformers, as the name suggests, contain two separate windings within a single unit. These windings can be configured in different ways to achieve various voltage and current outputs, providing flexibility in designing and powering low-voltage lighting circuits. One common application of dual-coil transformers is to supply power to two separate lighting zones or circuits. In this configuration, each coil operates independently, providing isolation between the circuits and allowing for independent control of the lighting in each zone. This can be useful in applications where different areas require different lighting levels or where it is desirable to be able to switch off the lighting in one area without affecting the lighting in another. Another application of dual coil transformers is to connect the coils in parallel to increase the total power output of the transformer. When the coils are connected in parallel, the voltage remains the same, but the current capacity is doubled. This can be useful when powering a large number of low-voltage lights or when the total wattage of the lights exceeds the capacity of a single coil. When connecting the coils in parallel, it is important to ensure that the coils are properly phased. If the coils are out of phase, they will effectively cancel each other out, resulting in little or no output voltage. To ensure proper phasing, it is important to follow the manufacturer's instructions and to use a voltmeter to verify that the voltage across the coils is additive. In addition to these basic configurations, dual coil transformers can also be used in more complex circuits to achieve various voltage and current transformations. For example, the coils can be connected in series to double the output voltage or to create a center tap transformer that provides both positive and negative voltage outputs. When working with dual coil transformers, it is important to understand the transformer's voltage and current ratings. The voltage rating specifies the maximum voltage that the transformer can safely handle, while the current rating specifies the maximum current that the transformer can deliver. Exceeding either of these ratings can damage the transformer and create a fire hazard. It is also important to consider the transformer's impedance when designing low-voltage lighting circuits. The impedance of a transformer is a measure of its resistance to the flow of alternating current. The impedance of the transformer can affect the voltage drop in the circuit and the overall efficiency of the system. In general, it is desirable to use transformers with low impedance to minimize voltage drop and maximize efficiency. When installing dual-coil transformers, it is important to follow all applicable electrical codes and safety regulations. The transformer should be mounted in a dry, well-ventilated location and should be protected from physical damage. The wiring should be properly sized and insulated, and all connections should be tight and secure. It is also important to provide overcurrent protection for the transformer to protect it from overloads and short circuits. The overcurrent protection device should be sized appropriately for the transformer's current rating. In summary, dual coil transformers offer a versatile and efficient way to power low voltage lighting systems. By understanding the different configurations and applications of these transformers, you can design and install lighting systems that meet your specific needs and requirements. Always follow applicable electrical codes and safety regulations when working with electrical equipment. Furthermore, addressing the specific scenario presented with one manufacturer stating a 300 watt maximum and another suggesting that looping increases the capacity to 600 watts, it is important to clarify the context of each statement. The 300 watt limit likely refers to the maximum load that can be safely connected to a single coil of the transformer. This is a fundamental limitation based on the design and capacity of the individual coil. The suggestion that looping increases the capacity to 600 watts is valid only when the two coils are properly wired in parallel and the total load on the entire loop does not exceed the combined capacity of both coils. In this configuration, the transformers share the load, and the system can effectively handle up to 600 watts. However, it is crucial to ensure that the wiring and other components of the loop are also rated to handle the increased current. To determine the correct approach for your specific application, it is recommended to consult the manufacturer's specifications for the transformers you are using. These specifications will provide detailed information about the transformer's voltage and current ratings, as well as any specific instructions for wiring the coils in parallel. It is also important to consider the specific requirements of your lighting system, such as the number and wattage of the lights you are using, and to design the system accordingly. If you are unsure about any aspect of the installation, it is always best to consult with a qualified electrician. Remember that electrical work can be dangerous, and it is important to take all necessary precautions to protect yourself and others from electrical shock. Always disconnect the power before working on any electrical equipment, and use appropriate safety gear such as insulated gloves and safety glasses. By following these guidelines, you can ensure that your low voltage lighting system is safe, efficient, and reliable.